So this is an attempt to give you an overview of using Anova and also multiple comparison tests if you happen to need to use a t-test to compare more than two groups. So the first thing we need to do is have a quick refresher about t-tests, and as you know, it's about comparison of means between two groups. They're parametric tests, so they assume normality. Anova is a parametric test as well, so you do need to have some view of normality. A t-test works on continuous data, so height, weight, glucose measurements, anything like that. But the key difference is that a t-test is always a two-way comparison. Anova is more than two-way. Okay, so it's A, B, and C. A t-test is A and B. So as you saw from the t-test video, to do a t-test in Excel, you'll get a probability result from 0 to 1. And 1 in this case is equal to 100%. We're comparing two groups here, the salmon pink and the blue. So the control and the test group. And what we're trying to do is find out what is the likelihood that the difference in the means is genuine, and what is the likelihood that it's a fluke. So if we get a value of 0.037, then that's equivalent to a 3.7% chance that what we observe in this chart is actually a fluke. And a 5% chance of being a fluke is kind of generally given the crude rule of thumb that would actually be good enough to accept if something is relevant or not. That's probably too generous. It probably needs to be much more stringent realistically to avoid the problem that's dogging a lot of biomedical research at the moment, which is the problem of irreproducibility. But at its core, what we're doing is identifying that there's a difference and giving a probability that that difference is true. Now, if we have more than three groups, so let's say we have group A as control, we have group B and C, both of which got different drugs to treat their cancer. Now we have a whole pile of different comparisons we can do. We have a total of 3 different comparisons. So that's 3 factorial divided by 2 factorial, which gives 3. Okay? So we have lots of different comparisons we can do, and the difficulty is that sometimes those comparisons will be significantly different and sometimes they won't. So if you look at these little grey lines, they're meant to be a kind of a shape of the distribution of each of these. And they're all basically normal because we're assuming a normal distribution. And for group B and group C, you can see that these distributions don't overlap. And if you ever have a situation where distributions don't overlap like that, it's highly likely that there is a significant difference between the two. Now if we take A and B, now in the previous one we said in A and B there was a 3.7% chance that the difference we observed is a fluke. And if we look at the distribution of these, you could kind of imagine, well, maybe there's a few samples that are overlapping. Are they overlapping enough? It's hard to see. But it's possible that these are from different populations. The problem, however, is that when we have multiple tests, doing a lot of comparisons means that we'll find something by fluke if we do enough comparisons. So just think about that for a second. If the threshold is 0.05 for p-value, which is equivalent to a 5% chance of a fluke, then each time we do that, we have a 5% chance of finding a fluke. So if we do enough comparisons, let's say 20, that's going to mean one of those 20 comparisons will definitely be significant statistically according to that measure, but it will just be a fluke. It will be a false positive. It's not what we're trying to get. We're trying to do the opposite of that. And this problem gets bad very, very quickly. Okay? We start to generate false positives very fast, and it's bad. So when we have a couple of tests at that significance level, we start to get an increased likelihood of finding something. So you can see that it goes up very quickly from 10%, 14 to 20%, basically meaning that in that comparison, we have a probability of finding some sort of difference, even though there's nothing there. And if we plot the number of decisions versus the probability of finding one of them being significant, you can see that as you increase the number, you're pretty much guaranteeing finding something when there's nothing. Okay? Which is why we don't want to do this. So one solution is to use a statistical compensation called the Bonferroni correction. And what that does is it scales down your threshold for significance depending on the number of groups you're comparing. So if you have 3 pairwise comparisons, you take your p-value and you divide it by 3. And that makes it harder to say the results are significantly different, but it compensates for this idea that you're more likely to get a false positive. So as you can see in purple there, if you have 4 groups, you have 6 possible comparisons. So you have to divide by 6 in that case. So what you'll end up with then is your p-value of 0.05 divided by 3, giving you a much lower p-value. And any comparison needs to pass that to be considered significant. So it does make it much more of a challenge to find significance. A potentially more sophisticated solution, though, is to use the Anova, or analysis of variance approach. So we're going to look at just one-way Anova in this case. And that tells you that there's some difference between your groups. So it's in that ABC example, there's a difference somewhere. Now, it's not going to definitively identify exactly where that difference is. You'll have to use a post hoc test to do that. We'll talk about that in a second. So Anova has a bunch of assumptions, and you can see those in the green box. Many of these are similar to t-tests, so independent variable, independent groups, no significant outliers, similar variances, and remember the variance is the square of the standard deviation, and they should be normally distributed as it's a parametric test. And ultimately what Anova does is it considers all the variability. So the variability between the different groups, how the groups are different from one another, and also the variability within a particular group. So whether it's ABC or ABCD. And that comparison gives you something called an F-stat, and that F-statistic, just like a T-statistic from a t-test, you compare it to a table. And that gives you an ability to determine if you have a difference or not. And once you've done Anova, that tells you that you have, and it's, let's say it's significant, that tells you there's something interesting to look at in more detail. And then you need to apply a post hoc test. And a post hoc test is something that you've not necessarily planned to do before you started working on the experiment. So you might make an assumption that you are going to test something using a t-test before you even start. Okay? Whereas with the Anova comparison, you don't know that you're going to find anything until you do the Anova. So you use a post hoc test. Tukey's HSD test is really a key one to do. And one of the things that, and it's very common, and really what it's doing is it's finding what's the kind of size difference or the distance between the means that has to be there before you can consider them significant. And to do that, you need a couple of things. You need the means of the treatment groups. You need the mean square within. So that's the differences within a group. And then you also need the number of samples that you've got in total. So what it looks like is that you need to first calculate the mean of A and the mean of B. Take B from A, and you divide that difference of means by the square root of the average sum of the squares between the groups divided by the total number of data points for the groups you're comparing. And then you're looking at it compared to a statistic, this case the studentized range Q-stat. You can find that online or in textbooks, and if it's above the critical value, then you can deem it to be significant. We will come back to doing some of the Anova stuff and what it looks like in Excel and other applications later on, but this is just a kind of conceptual overview of what you're doing.